With my friend Mr. Ramgopal from University of Alberta, and he will entertain us on aluminum today. And please give him a great round of applause, and we'll start the conference right after. Thank you very much.
Thank you, everyone. My name is Rishikesh Ramgopal. I'm a master's student at the University of Alberta. I work with Dr. Patricia Mendez. I am going to talk about deposition rate in gas metal arc welding of ER1100 and 5183 aluminum alloys. So, the objective of what I'm trying to accomplish is that to understand why aluminum alloys that contain magnesium in particular tend to have a higher deposition rate, and to understand the reason behind it as well. The current hypothesis, which is believed to be the reason, is higher resistivity. So magnesium has a higher resistivity than aluminum as a whole, and aluminum alloys that contains magnesium tends to have a higher electrical resistivity, and this higher electrical resistivity will likely cause a higher joule heating, and this higher joule heating would provide the wire more power to melt easily, and this could be the reason behind the higher deposition rate. And in my process, we are going to check if that is the scenario or not. So the current knowledge. So with magnesium, like I have two plots which shows the wire feed speed versus welding current for 4043 and 5356. One has 0.03% magnesium and the other has 5% magnesium. These both are taken from the gas metal arc welding of Lincoln Electric, and you could see there is an increase of around 7.1% in wire feed speed with an increase of 5% magnesium. So this is already known, but I just wanted to show that it is already widely established as well. So for the approach, I take a two-step approach in which first one is the experimental aspect, in which we consider two alloys, one with and without magnesium, to understand the impact of magnesium, and we also measure the current, wire feed speed, and the droplet temperature. And in the analytical aspect, we calculate the electrical resistivity for both the alloys. We also perform an energy balance of the entire system to understand how much is the power necessary to melt the wire, one aspect. Second thing, to understand how much power would be generated through joule heating, and would the joule heating value be sufficient to take care of the power necessary to melt the wire, and is there any other additional effect which we are not considering. So for this process, we select two alloys, which is 1100 and 5183. I chose these two alloys in particular because, so you could see that 1100 has 99% aluminum and 5183 has 94.17%, but the remaining 5% is made up with magnesium. So these two alloys were selected in particular because this will give us a good understanding of the effect of magnesium. So for the experiment, some of these have already been spoken about in the past presentation, but I will still like to give it a good depth about it. So we use gas metal arc welding for the process, in which we obtain the current, the wire feed speed, and also the droplet temperature. We have the constant electrode extension for all the experiments done, which is 0.5 inches. And so for our droplet temperature measurement as a whole, we use a solid state copper calorimeter. And here is the setup which was used. The way we calculate the temperature as a whole is, once the molten droplet falls onto the solid state calorimeter, we have thermocouples fitted into the calorimeter, around 4 thermocouples. The copper calorimeter is designed in such a way that its Biot number is very low, in the range of 3.5 into 10 power minus 4. So the low Biot number of that calorimeter helps it to have a temperature homogeneity across the entire surface. Thus, any temperature which is measured across all the thermocouples is supposed to be very close representative of the actual temperature of the droplet which falls into the calorimeter. So just letting you know, that is not the actual droplet temperature, but just the temperature once the droplet falls into the calorimeter. So to talk about this, shows the results of the calorimeter, the data recorded by the calorimeter once the molten droplet falls into it. Here I don't consider, because I have 4 thermocouples, I'm able to average the results of all the 4 thermocouples to give an actual number which is which is a very good representation of the overall temperature of the calorimeter. And so this is just an example of for ER1100 in wide field speed 160 to show that we also consider for the heat losses and we account for a temperature which is more or less a very good approximation of the of the temperature of the calorimeter. So the way we do our droplet temperature measurement is based on a mass and energy balance of the initial phase. This is the initial phase in which we have the hot incoming droplets fall into a cold calorimeter, and then to the final stage in which the droplet and the calorimeter reach a thermal equilibrium. So these 2 stages are selected in such a way that any stage which happens in the center can basically be ignored, because if we are doing a mass and energy balance, it's not lost. So from the initial stage to the final stage, it will give us a very good approximation of the droplet temperature. Not approximation, very good estimate of the droplet temperature. Based on that, we have the energy balance of the droplet and calorimeter shown here from the initial stage to the final stage. Then we are also able to find the enthalpy difference of the droplet, initial and final. So based on all of them, we are able to get the actual droplet temperature TDI, which is based on the enthalpies, specific heat, and the final temperature of the calorimeter as a whole. So since this requires a lot of thermophysical properties, we obtain all of them using GMAW Pro and ThermoCal. We use these 2 softwares in which I take the data from GMAW Pro, verify with the data from ThermoCal, and in my particular scenario, since I'm using aluminum alloys particularly, I correlate these alloy properties with the ASM handbook for aluminum alloys, and we chose the most representative thermophysical property for each alloy. So we could say that the thermophysical properties would not have a huge error at all. And so based on all of them, we are able to calculate the droplet temperature. And so the ones marked in blue squares are 1100, and the ones marked in orange triangles are 5183. And I have a moving average of 2 points trend line so that we can understand the trend as a whole. You could see that the difference between, you could see that 1100 alloy, which is just pure aluminum, tends to have a much higher droplet temperature across the entire current range. And the difference is not even small. It's it ranges from around 200 degrees Celsius to around 400, 500 to 500 degrees Celsius over here. So you could say they both have a pretty solid difference. And here we also use high-speed video footage, high-speed video camera, to understand what is the transfer mode during our process. So we are able to understand that over here, this is globular, moves onto a transition region, becomes a spray mode across the increasing current. In a similar scenario, we had globular, then we had a transition zone, and then to spray after increasing current. Thing is, both these alloys have a very similar transition zone where they switch from globular and spray. And I found that pretty interesting. So, next, the wire feed speed. We know that the wire feed speed of the alloy which contains magnesium, which is 5183, is supposed to be higher, and that's exactly what was measured. Here we had 5183 mentioned by the orange circles, tend to have a much higher, higher wire feed speed than 1100 across the entire current range. And since it's expected, we just moving on. Electrical resistivity. So we also calculate the electrical resistivity for 1100 and 5183. And as expected, the alloy 5183, which has magnesium, tends to have a higher electrical resistivity shown by the green dotted lines. And 1100, which is just pure aluminum, tends to have almost a very similar electrical resistivity across the increasing temperature. But we found that the electrical resistivity of 5183 tends to come closer to 1100 at lower temperatures. And this was based on the fact that magnesium splits out and is not present in the solid solution anymore, thus having a similar electrical resistivity to that of a pure aluminum alloy. And so for the analysis, in our first step, we have to find how much power is actually provided to the wire to melt it. That is represented as QD in our process. Next we find delta QD. So the reason we find delta QD, so first let me tell you what is delta QD. It is the power necessary to melt the wire for 5183 minus the power necessary to melt the wire for 1100. So the reason we find a difference is to understand how much extra power is necessary to melt 5183 over 1100. And the same way we'll be finding the difference from Joule heating to know if the effect from Joule heating can make up for this extra power, delta QD. So for this, we again do energy balance of the initial stage in which we have just a solid wire, which is at room temperature T0, to molten droplet, which is the next step. So this is the initial stage and that is the final stage. And once we perform the energy balance, which is the Q in minus 2 equal to Q out, we can say that the QD is the power delivered to the wire to melt it, and then the initial stage to the final stage. Then we find the difference in enthalpy of the droplet, enthalpy of the wire, subtract it, and then we are able to find the power necessary to melt the wire, QD. So this QD is dependent on the density of the wire feed speed, and the area of the consumable, and the droplet temperature. So our second step of the analysis is to understand the power generated through Joule heating, because that is what we are trying to correlate and to check if this makes up for it. So we also find delta QE. So this is again the power generated through Joule heating for 5183 minus the power generated through Joule heating for 1100. And when I'm talking about Joule heating, I'm also talking only at the electrode extension. So here, the QEE is dependent on the effective resistivity, the electrode extension, current, and the area of the consumable. So, the results of the Joule heating, which is 1100, is represented by the blue triangles, and 5183 is mentioned by the orange circles. And this is as expected, which is the Joule heating value of 5183, which contains higher electrical resistivity, is going to be higher. And that is true. It's higher across all the current ranges. But the point to note is the difference between both of them, between 1100 and 5183, is pretty small. So that's approximately 0.3 watts in the initial stage and 1.8 watts in the final stage. So this is the maximum difference in Joule heating generated for both the alloys. Now, when we compare it with the actual power necessary to melt the wire, QD, here we have the 5183 is mentioned by the orange circles and 1100 by the blue triangles again. Here you can see that in the initial scenarios, you can see 5183 is lower than 1100 except at 120 amperes. But after there's a switch in which 5183 becomes higher all the way up to increasing currents. So we have an initial lower power to melt the wire for 5183, then it switches and then it needs a lot more power than 1100. So that's just the only point I want you to remember. So now we can actually compare the results of and the Joule heating impact. So this graph shows the energy with current, and it represents two things, which is delta QE and delta QD. So delta QE again is the Joule heating difference between 5183 minus 1100 and the electrode extension, and delta QD is the power necessary to melt the wire for 5183 minus 1100. So here, what does a negative delta QD mean? Okay, before I get to that, you could see that there is delta QE is 0. So, frankly, it's not actually 0. It's just that the scale is so much smaller than delta QD, which is in the order of hundreds of watts, that the actual value of delta QEE, which is around 0.3 to 1.8 watts, looks very small. That's the reason it's represented close to 0. Now when we talk about why we have a negative delta QD, in that scenario, that means 5183, the wire which has higher deposition rate, needs lesser power to melt the wire than 1100. So let us talk about this scenario. A wire like 5183 has lesser power delivered to it. It still has very high wire feed speed. And what could be the reason? Because if you provide similar power, then it might be, we can think of some other reason, but when you have this lower power delivered to 5183 and it has a higher wire feed speed, the only reason it could be is because 5183 also has much lower droplet temperature than 1100. So the lower droplet temperature of 5183 can explain why we have a high wire feed speed even when we have a high wire feed speed, even though lesser power is delivered to it. But on the off scenario, after 150 amperes, you can see delta QD is much higher. And in that scenario, the droplet temperature cannot explain it, but the alloy actually has a lot more thermal energy than what is provided through Joule heating. So what we could conclude from this is that Joule heating at the electrode extension cannot be the cause behind the higher wire feed speed observed in magnesium containing aluminum alloys. But the lower droplet temperature can explain it at currents below 140 amperes, but at the higher current ranges, the alloy has a lot more thermal energy that can be accounted through Joule heating. So to discuss, I would like to talk about the reason we have a lower droplet temperature in 5183 could be attributed to the fact that magnesium boils at 1091 degrees Celsius, which is really low compared to our high droplet temperatures. And this boiled magnesium could cause a local thermal balance around the droplet, forming it to have a lower droplet temperature. And the higher thermal content of 5183. So based on the energy balance with Joule heating at the electrode extension, the thermal energy from the contact tip and the contact resistance, we could say that the cause behind the higher thermal content would be mostly due to the anode fall voltage. But how it actually affects it is because the shielding gases which we use and the metal vapors of magnesium and aluminum, as said in the last presentation, that magnesium and aluminum both evaporate to a very high extent at high currents, we can say that these vapors could impact the sheath or pre-sheath fall. And also magnesium has a higher ionization energy than aluminum, all of which could play an impact, causing it to have a higher thermal content, but that is yet to be researched fully. So, to conclude, I would like to say that the difference in Joule heating and electrode extension cannot explain the reason behind the higher wire feed speed we have in magnesium containing aluminum alloys. But the lower droplet temperature can explain the higher wire feed speed below 140 amperes. At intermediate currents, we still need more. We still need to understand why we have this higher thermal energy. That is part which is yet to be discussed further and researched further. So thanks to Lincoln Electric and INSET for funding.
Thank you very much for that presentation. Does anyone have any questions for our speaker? No questions?
Thank you. That means I did great.
You did great. Yeah. Aluminum is always that touchy subject.
Awesome. Thank you, everyone.
Thank you very much for your presentation. A token